Okay, this is a particularly challenging UT Quest assignment. This is kind of a Attwood's machine with an inclined plane. But the way we're going to deal with this problem is we're going to treat it just like we do an Attwood's machine. What we're going to do is we're going to consider these three masses as one system. And the chord here are just internal forces. So let's take a look and see what forces are acting on the mass of this system. Well, I've got the weight of mass number 3 pulling the system one way. I have the weight of mass 2 pulling the system the other way. I have the mass of 1, and it's going to have some friction force that's going to pull the system this way, or try to. And then this will have a component of its weight trying to pull the system this way. All right, so what we're going to do is we're going to just resolve these tug-of-war forces and treat them like they're acting on the entire system. Okay, so let's take a look at this guy right here. And let's do a free body diagram of here and see what's going on. Now, just by inspection, I'm making the assumption, since this is such greater mass than these two, the system will probably accelerate down this ramp. Okay, so all these forces are going to be doing one of two things: trying to pull the system up the ramp, trying to pull the system down the ramp. All right, let's take a detail at mass number 1. Okay, at mass number 1, okay, I'm assuming that it's trying to slide down the ramp this way, so that means it's going to have this force of friction opposing that. Mu k given. Now I got to figure out force normal. I am on an incline. But I do have theta, and I do have this mass. So here's the weight of mass 1. I break it into perpendicular and parallel components. This vector and this vector are going to be in equilibrium. So that gives me force normal that I'm able to use in this equation and find force of friction. This guy here, this is a force vector that's going to be acting in the direction of acceleration. And I'm going to have to account for that guy. All right, now I'm ready to look at all the forces acting on the entire Attwood system. So let's consider these three masses together as an entire system. Some of the forces are trying to pull it up the ramp. Some of them are trying to accelerate the system one way. Some other forces are trying to accelerate the system the other way. All right, as we can look here, all right, this guy is trying to pull the system this way. This guy is trying to pull the system this way. So let's start with those two forces. These are easily calculated. I don't know each of these masses. I'm given G, so I can easily compute this guy and this guy. From my free body diagram of mass 1, I got this force of friction, and then I have to be very careful to include this guy right here. All right, M1 does have this component of weight that is acting to pull the system down the ramp. So I really have 4 forces acting on this composite system. But now I'm ready to go to Newton's second law. As long as I calculated the values of each of these forces correctly, I've got 2 of these forces trying to pull the system one way, 2 of these forces trying to oppose what these guys are doing is equal to mass times acceleration. And then I can solve for acceleration. All right, now, last but not least, let's look at some of the internal forces. Okay, so they ask us to look at this internal force right here, this tension pulling on this mass right here, what we're calling M3. And no, this and this are not equal because this is accelerating upward. So I need to account for that in my free body diagram of the third mass. This is easily computed. Notice how I've drawn this internal force of tension on this piece of the rope as being greater than the weight of mass 3. That's because this must accelerate upward. And we've already computed the magnitude of that acceleration. So I'm going to have the force of tension pulling up. I'll call that positive. I've got the weight pulling down, I'll call that negative, is equal to mass of 3 times the acceleration of mass 3, which is the acceleration of the entire system, and then I can calculate the force of tension. Just be very careful with your numbers and your round-off error, and you should be good to go on this problem.